I'm Dane Quinn from the University of Akron, and today we'll do another example on rigid body dynamics. So we have a pulley system as shown to the right, and each pulley has mass M1 and radius R. So the two pulleys are identical, while the block has mass M3 and hangs down and is subject to the influence of gravity. The left pulley is also subject to a force minus F in the J direction. So we have a force on the left pulley that's pulling down, and I'd like to find the resulting acceleration of the block. So we will start off and identify the forces that act on these pulleys, these objects. So we certainly have the applied load minus F in the J direction, as given in the problem statement. Then we have the weight acting on each object, right? So we'll call this W1. We have the weight acting on the second pulley, so that's W2. And we have the weight acting on the block, W3. So we'll denote these objects as 1, 2, and 3. Now, we also have the tension in the cable. Right, so this cable wraps around the first pulley, around the second pulley, and then is attached to the block. So on the first pulley, on the left, we'll define this as T1. We'll define the tension on the right of the first pulley as T2. Now, again, this second cable is attached to both. Right? So really the idea here is that we're cutting the cable here, and we're looking at the force that acts on the lower and upper pulleys. So if this force is T2, so this force is minus T2. These two forces have to be of equal magnitude and opposite direction because it's an internal force. It comes from a cut to the cable. So the two forces, when taken together, have to balance one another out. Likewise, on the right pulley, we have a force, and we'll say minus T3 acting on the pulley, and then plus T3 acting on the block. Again, the important thing here is that these forces have equal magnitude and opposite direction, so they're related. If this one's T3, this one has to be minus T3. Finally, we have a reaction force from this support for the upper pulley, and we will label that as R. So again, the forces arise from the tension in the cable, and that's T1, T2, and T3. Then the reaction force, and that we've denoted as R. The weight of all of the objects, so W1, W2, W3, and finally the external force. That was given to us in the problem statement as minus F in the J direction. Again, this minus sign indicates that if F is positive, the force is pulling down. So here at this step, we're just trying to identify what forces act on the system. We're not necessarily saying what they are, or we're not trying to give directions or anything. We're just trying to say that they're there, which will help us to identify the coordinates and directions that we may need to solve this problem. So now let's turn to that, coordinates and directions. Remember that the coordinates are measurable quantities that help us identify the configuration of the system. And the directions are, whatever directions are relevant to the motion and the forces. So the problem statement gave us I and J as horizontal and vertical directions, and that's probably okay. All the forces, all the motion is in the it's in the J direction. I sort of comes along for the ride. Now we need to define coordinates that will help us to measure the configuration. So what do these objects do? Right, that's kind of the crucial question here. Well, the block moves up and down. The upper pulley simply rotates. Note that its mass center is fixed through this cable, so all it does is rotate. While this pulley both moves up and down, right, and rotates. So let's look at this, and we will measure the vertical displacement of the pulley as x, and the rotation of this pulley as theta. Then, for this pulley, it only rotates, right? So we'll measure its rotation with an angle phi. And then finally, the block can move up and down, so we will measure the motion of the block, the displacement of the block, with y. Here I'm sort of assuming that x and y and theta and phi are all measured from a common configuration, which implies that all of those coordinates vanish at exactly the same place. Right? So if there's some configuration for which all of those coordinates are 0. So now, with these coordinates, we can fairly easily go and describe the kinematics of the system. Again, I mean, that's kind of why we defined as many coordinates as we did, because we wanted to make this step easy. So let's identify some important points. A will be the center of this pulley. B will be a point on the block. Then we'll also measure a point here on this cable as O1, and then the center of this pulley will be O2. Notice that I'm using O to denote points that are fixed in the ground. So every point on the cable to the right has 0 velocity, right, because they're all fixed in the ground. Likewise, every point on this cable, including the center of the pulley, is fixed in the ground. So they all have 0 velocity. So last, we will identify the point on the part of the cable connecting these two pulleys as C. And we'll use all of these points when we end up relating the kinematics of this system. But for now, let's go through and define the acceleration, both linear and angular acceleration, of each object. So if I look at pulley 1, which we will distinguish as the left pulley, we find that the acceleration of its mass center, namely A, is x double dot in the j direction, while the angular acceleration of pulley 1 is described by this angle theta as theta double dot in the k direction. And so we have the linear and angular acceleration of this pulley. For pulley 2, notice that the acceleration of the center of pulley 2, so that would be AO2, is equal to 0, because this point O2 is fixed in the ground. Then, the angular acceleration of pulley 2 is phi double dot in the k direction. Finally, we have the mass, or the block. And for that, the acceleration of B is equal to y double dot in the j direction. So now we need to look at kinematics of this pulley system, because these coordinates are related. Right? X is related to y and theta and phi. So now we can describe those relationships with equations for the velocities of these various points. So as we've done for the kinematics of pulley systems, we look at pulley 1, and we see that the velocity of A is the velocity of a point on the left, which is O1, plus the velocity of a point on the right, C, divided by 2. For the second pulley, we have a similar relationship. Velocity of the center is the velocity of the left, where the left is point C, plus the velocity of the right, which is point B, divided by 2. So I can actually take these expressions and eliminate the velocity of C. Because here the velocity of O1 is equal to 0. The velocity of O2 is equal to 0. So both of those points are fixed in the ground. So from this relationship, we find that the velocity of C is minus the velocity of B. And then when we introduce this into the first constraint, we see that the velocity of A is the velocity of C over 2, but that becomes minus the velocity of B over 2. Now turning to the coordinates that we've defined, the velocity of A is equal to x dot in the j direction, and that's going to be minus the velocity of B, which is y dot in the j direction, divided by 2. So finally, taking components in the j direction, we see that x dot is minus y dot over 2. So that's our relationship between x and y. So likewise, we can relate the rotation of each pulley to some combination, some appropriate value of the displacement. So let's look at pulley A. So here we have that the velocity of A is the velocity of O1 plus the angular velocity of pulley 1 cross R A O1. Because this point O1, and again we're thinking of this point O1 as being here where the cable also comes into the disk. This cable doesn't slip on the disk, so the velocity of this point is 0. Now that implies that x dot in the j direction is 0 plus the angular velocity, which is theta dot in the k direction, cross A with respect to O1, so that's R in the I direction. So x dot is equal to, well, k cross I is j, so we have R theta dot in the j direction, which means that x dot is equal to R theta dot. So now, on pulley 2, we can relate the velocity of the center of the pulley to the velocity of a point on the right of the pulley, which is identical to the velocity of the block. Right, so we'll identify this point as the velocity of B. And so the velocity of B is the velocity of the center of the pulley plus the angular velocity of the pulley across the position of B with respect to O2. So now the velocity of B, again, was y dot. The velocity of the center is equal to 0. The angular velocity is phi dot in the k direction, cross R in the I direction. So again, the vector from O2 to B is Ri. So that reduces to y dot equals R phi dot in the j direction. So this constraint is that y dot is equal to R phi dot. So now we're at the point where we would like to finish up the free body diagram and apply the equations of motion. So once again, looking at these forces, we had force here, which we will define as T1 in the j direction. So now we're explicitly using directions as we've defined I and j, and then unknown values for the tension as they relate to the forces. So this force was T2 in the j direction. We have the weight as minus m1g in the j direction. And we have the applied load minus F in the j direction. This force then is minus T2 in the j direction. This force we defined as minus T3 in the j direction. We also have the reaction force, and finally the weight, which again was minus m1g in the j direction. On the block, we have T3 in the j direction, and we have the weight, which was minus m3g in the j direction. So we've gone back to our force diagram, which we did initially, and we've kind of completed this with proper descriptions of these forces: tensions, the weight, the reaction force, whatnot. And so now, turning to the equations of motion, we apply momentum balance to each object in the system. So in particular, for pulley 1, we have linear momentum balance as sum of the forces acting on this object, which is T1 in the j direction minus m1g in the j direction plus T2 in the j direction minus F in the j direction equals m1, the mass of the pulley, times x double dot in the j direction, which is equal to the mass of the object times the acceleration of the mass center. Then, angular momentum balance is the sum of the moments about A, and again remember that A is the mass center of this point, equals, well, the moments produced by all of these forces. Notice that the applied force acts through A, as does the weight, so they produce no moment about the mass center. So the moment produced by T2 is R times T2 in the k direction, and the moment produced by T1 is minus R T1, and both in the k direction, which is equal to the moment of inertia of this disk, m1 r squared over 2, times the angular acceleration, which is theta double dot k. So again, this is I of body 1 about A times alpha 1. Moment of inertia times angular acceleration. So then for pulley 2, the equations of motion, particular momentum balance, is the sum of the forces. Again, this is linear momentum balance. All the forces acting on body 2, so that's minus T2 in the j direction, plus R in the j direction, minus T3 in the j direction, minus m1g in the j direction, the weight, equals the moment of inertia, equals the mass of the object times the acceleration of the mass center. But recall, this point was O2, and O2 is fixed in the ground. So the acceleration of this object is 0. So the total force acting on body 2 vanishes. However, the angular momentum balance equation is not nearly so simple, right? Because the object does rotate. So we have the sum of the moments about O2 is the net moment. Again, the reaction force and the weight act through the mass center. So we have a moment T2 times R produced by this force, and then the moment produced by T3 is minus T3 times R. And I will remind you that moments produced by forces are defined as R cross F. So for example, T3, it would be the position of this point where T3 acts with respect to O2, Right, so that would be like r in the I direction, cross the force minus T3J. So that produces a moment minus T3 times r in the k direction. And this is equal to the moment of inertia, mr squared over 2. Recall that each of these disks are identical, so the moments of inertia are identical. But the angular acceleration here is phi double dot in the k direction, because phi describes the rotation of that disk. Finally, on the block, we have linear momentum balance as some of the forces. And this is simply T3 in the j direction minus M3G in the j direction is equal to my double dot in the j direction. So again, sum of the forces is mass times acceleration. So these are the equations of motion. We have linear and angular momentum balance on pulley 1, linear and angular momentum balance on pulley 2, and then linear momentum balance on the block. Notice there's no angular momentum balance because there are no moments produced and the block doesn't rotate. So really, sum of the moments is equal to 0, I alpha is equal to 0. So linear or angular I alpha is equal to 0. So angular momentum balance simply reduces to 0 equals 0, which of course is a valid equation, but not terribly interesting or useful for the solution to this problem. So now we will take components. Taking components of all of these equations yields the following. And these are now scalar equations that describe the response of the system. So for the pulley 1, in linear momentum balance in the j direction gives me T1 plus T2 minus M1G minus F equals M1X double dot. And we have R times T2 minus T1 equals M1 R squared over 2 theta double dot. For pulley 2, we can write R minus T2 minus T3 minus M1G equals 0. So this was linear momentum balance in the j direction. And R times T2 minus T3 equals M1 R squared over 2 phi double dot. Finally, for the block, we have T3 minus M3G, the weight, equals M3 Y double dot. And recall we also have constraint equations. So we have relationships between x and y and phi and theta. So once again, those are y dot is equal to minus 2 x dot. X dot is equal to r theta dot, and y dot is equal to r phi dot. Now, the nice thing is that these constraint equations I can take derivatives of. Here we find that y double dot is minus 2x double dot. X double dot is equal to r theta double dot. And y double dot is equal to r phi double dot. So we can use these constraint equations as written on the accelerations in our equations from momentum balance. So we need to solve these. Notice that we have 1, 2, 3, 4, 5, 6, 7, 8 equations. And I have a number of unknowns. I have T1 and T2 and X double dot, that's 3. I have theta double dot, that's unknown number 4. R, number 5. Phi, number 6. T3, number 7. And Y double dot, number 8. So I have 8 equations and 8 unknowns. I can solve these. Unfortunately, it's not so bad. So eliminate the unknown tensions from the equations for momentum balance. So looking at this, I can take this equation and solve for T3. Then I can use that and solve for T2. Then I can use that and solve for T1 here. I can take those expressions for T1 and T2 and introduce them into this equation. So in doing so, I have eliminated the unknown tensions. And this equation, when I do that, becomes M1G plus F minus M1 X double dot plus M1 R over 2 theta double dot equals 2 times M3 G plus M3 Y double dot plus M1 R over 2 phi double dot. And so here we have an equation that really only depends on the coordinates. And now I can use my constraint equations to solve for y double dot. So in doing so, we end up with y double dot equals F plus, and then M1 minus 2 M3 times G, and all of that divided by 4 M1 plus 2 M3. Now obviously there's a lot of algebra that goes into all this, making these substitutions and solving for these various things. And so maybe you can pause the video solution at this point and work through that algebra. But ultimately, you should be able to find this expression for y double dot. And then recall that what we wanted was the acceleration of the block. So that the acceleration of the block was defined as y double dot in the j direction. And y double dot is F plus M1 minus 2 M3 divided by G divided by 4 M1 plus 2 M3 in the j direction. So again, we are able to solve for the acceleration of the block for this system. So there we have it. The acceleration of the block is given in this expression. And again, there's a lot of algebra here that you should probably pause the video solution and work through. But this is the answer that you should get. So here, the kind of important thing that we've done here is looked at a problem with a pulley system in which the pulleys have mass. So we have to look at the dynamics of each pulley, each component. We also have to consider the constraint equations that are introduced by the cable. But putting that all together, we get, as we see here, we have a number of equations that arise from momentum balance, laws of motion applied to the objects. And then we have a number of equations that come from the constraints that arise from the pulley system. And we combine all of these things ultimately to solve for the response of the system. And in this case, the acceleration of the block. So that's a pretty good example that has lots of different parts and pieces in it. And thank you very much. I will be back.